Alright everybody, welcome back. This is our second video on section 8.7 of AP Calculus, volumes with cross-sections, squares, and rectangles. In the last video, we introduced a general methodology and talked about how to set up finding volumes of cross-sectional solids. In this video, we're just going to go ahead and do a couple more examples, and we'll start with example 3 here, which comes to us courtesy of the 2011 AP Calculus AB exam Form B. So it's free response question number 3, which is a non-calculator question. All right. The functions f and g are given by f of x equals square root of x and g of x equals 6 minus x. Let R be the region bounded by the x-axis and the graphs of f and g as shown in the figure below. The region R is the base of a solid. For each y, between y equals 0 and y equals 2, the cross-section of the solid taken perpendicular to the x-axis is a rectangle, whose base lies in R and whose height is 2y. Write, but do not evaluate, an integral expression that gives the volume of this solid. So first of all, this region R forms the base of our solid. So you can imagine our solid coming out of the, out of the paper or out of the screen, where the base of the solid sits in this region R. For every value of y between 0 and 2, so every value of y along here, the cross-section perpendicular to the y-axis. So for instance, this cross-section right here is perpendicular to the y-axis. What I would have coming out of my screen here is I would have a rectangle coming out of my screen here as this part of this solid. So that's what my cross-section looks like. It looks like this. Okay, so the base lies in R, and the height is 2y. Now, since this cross-section is perpendicular to the y-axis, this is something that we didn't talk a whole lot about in the first video. When our cross-sections are perpendicular to the x-axis, then we want our integrand and our limits of integration to be in terms of x. When our cross-sections are perpendicular to the y-axis, we want our integrand and our cross-sections to be in terms of y. We kind of mentioned it quickly in passing in the last video, but that's something that you need to be aware of. So we're talking about perpendicular to the y-axis. So we want everything to be in terms of y when we set up our integral expression here. Now the only thing I need yet is I need an expression for the width of this rectangle. And this rectangle goes in between the curves y equals f of x and y equals g of x. However, I know both of those curves as functions of x, and I need to go ahead and get them to be functions of y to represent what's going on here. So I've got y equals the square root of x is this curve. If I solve that for x, then x is equal to y squared. So y squared is what I want to represent this curve in my expression. And then y equals g of x is 6 minus x, so y equals 6 minus x. If I solve that for x, I just get x equals 6 minus y. So 6 minus y is this expression. So that means that for a given rectangle, the distance from here to here is going to be 6 minus y, the right endpoint of this line, minus the left endpoint of this line, gives us the length of this line segment here. And so the width of my rectangle is 6 minus y squared. All right. And now I can set up and find the volume of this solid. The area of one of these rectangles in terms of y is 2y times the quantity 6 minus y squared. So I'm going to have the integral of 2y times the quantity 6 minus y squared with respect to y. And now all I need are my limits of integration. And my limits of integration are going to go from the bottom end at 0 up to the top end at 2. And there is my expression for part B. All right. Example 4 from the 2015 AP Calculus A/B exam free response question number 2. This is a calculator question. Let f and g be the functions defined by f of x equals 1 plus x plus e to the x squared minus 2x, and g of x is equal to x to the fourth minus 6.5x squared plus 6x plus 2. Let R and S be the two regions enclosed by the graphs of f and g in the figure below. And then we're going to answer question B here from this question. Region S is the base of a solid whose cross-sections perpendicular to the x-axis are squares. Find the volume of the solid. So we've got a square. We just need to know the length of the side of the square. And do I know which curve is which here? I believe that this top curve here is the x to the fourth minus 6.5x squared plus 6x plus 2. And the other curve is my line plus exponential. Okay, so the upper boundary of this region is g of x. The lower boundary of this region is g of x, because g of x is on the bottom over here. And the upper boundary is f of x. So that means that the length of one side of this square is going to be f of x minus g of x. And when I set up my integral in the end here, I'm going to put f of x and g of x in it, but that's the length of a side, which means that the area of this square is going to be the quantity f of x minus g of x, quantity squared, because that's how we find the area of a square. All right, so to set up my integrand, I'm going to have the integral from one end of the region to the other in terms of x. We know the x-coordinate of this endpoint is 2. This endpoint we're going to have to find, but this is a calculator question, so that's not going to be hard for us. And then I've got the expression f of x minus g of x that whole quantity squared. That's the area of one of those squares. And now I need to do two things. I need to find the intersection point of these two curves. And then I need to integrate. So let's type those functions in. I'm going to type them in order, because then I can use a little trick on my calculator. X to the fourth minus 6.5 x squared plus 6x plus 2. Okay, and now I'm going to graph these two curves. And I see this region right here is what I'm looking at. So I'm just going to use one of my favorite zooms. I'm going to zoom box in on this thing. Put a box around what I want to look at. This is what I want to look at, because this very closely will resemble what's on my paper. There we see that. All right, and now I want to find my intersection of those two curves. First curve, second curve. Move my cursor over. And so the x-coordinate here is going to be my lower limit of integration, 1.032 8319. All right, and something that I can do to save myself some typing on my calculator, and I can show you how to do it on your calculator as well, is when I go to integrate this, since I typed these functions into the graph screen in order to graph them, I can set up, and I can actually just say, okay, I put this function in y1, so I'm going to type y1 of x, and it's going to pull that function out for me. And the second function is y sub 2 of x. And I'm not going to forget to square that whole thing because of what my integrand is. And then I am going to take that with respect to x and my limits of integration. And I can calculate the volume of this solid. Give my calculator some time here. There we go. We get 1.283 for the volume of this solid. Now, for those of you who use the 83 style calculator, something that I can do is once I type these functions in to find the intersection points, I'm going to show you exactly how I did it on my calculator. Where's the e? There it is. E to the x squared minus 2x. One of the reasons why I use my other calculator all the time is, for some reason on my computer, this calculator always requires me to double tap every key in order to get what I want, whereas my other calculator only requires me to single tap. And sometimes when I double tap, it doesn't catch either. Alright, so I've got those curves typed in. I can go out to my main screen, do math 9, and now I wanted y1 minus y2 inside of the parentheses here. I can pull those out from my vars menu right here. If I go to vars, go over to yy vars and choose function. y1 is the first one in there. I can bring that out to the main screen. Minus, go to my vars screen, grab y sub 2, and square that expression with respect to x from 1.0328319 to 2. And you can certainly do this anytime you're putting functions into your calculator in your graph screen. Notice we get the same volume as we should. Anytime you're putting two equations into your graph screen, you can use this kind of concept to save yourself some typing when it comes time to find your integral. Just make sure if you're going to do that you keep track and keep straight which curve is which. In this particular problem, it would not have mattered, but there will be some problems where it does. All right? Okay, that's it for this lesson. We should be to the point now where we've got some practice problems to do and get this topic really under our belt. Come back and join us next time. We're going to be talking in section 8.8 where we're going to be doing volumes with cross sections again, only this time with triangular regions and semicircular regions instead of squares and rectangles. All right, everybody, have a good rest of your day, and I'll see you next time. Bye-bye.